pleasure to introduce the first speaker this morning, Asaf Nachmias. We'll talk about uniform spanning forests of planar graphs.
Hello, thank you for the introduction and the pronunciation of my name. And thanks for the invitation. It's nice to be here. So I'm going to talk about this picture, which is in focus. I'm going to talk about, I'm going to tell you a story about spanning forests on planar graphs. So spanning forest is just a subgraph of your graph that has that contains all the vertices and has no cycles. And in this picture, you can see this is a picture I shamelessly stole from Yuval Peres and Russ Lyons. I did not generate this picture, nor do I know how to, but I can tell you what it is. This is a planar Cayley graph, and what you see in thick lines is a spanning forest of it. Inside and in the thinner lines is the dual forest, right? To every edge of the planar graph that exists, the dual edge does not exist, and vice versa, right? And if you have a spanning forest of a planar graph such that all the faces are bounded, you can draw the dual forest just like that. So there's a one-to-one mapping that generates one from the other. And in this picture, you can see, and I'll leave it on so when you're bored, you could just stare at it. You'll see that the thick one is actually a connected span. It's a spanning tree of the graph. I stared at it for at least half an hour to fall asleep last night, and I think it's really connected. While the thinner one is disconnected, this is more easy to see, and it has many components that are all infinite. They're not connected, and the special thing about them, if you'll notice, is that they do not have any bi-infinite path, which is easy to believe if you believe the first statement that I made, that if the thick one is connected, then the dual one cannot have a bi-infinite path. And something that I will also tell you, though I have no idea whether it's true or not, that this was generated randomly this is in some sense a random uniform spanning forest. So of course, when we have a finite graph, so let G be a finite graph, and I want to mention, by the way, that this is all joint work with Tom Hutchcroft from UBC. And please stop me if you have any questions or concerns, jokes, mockery. Let G be a finite graph. Right, our goal is to draw a uniform spanning tree or forest on an infinite graph, and what we're going to do, obviously, is take exhaustions and take uniform spanning trees on the finite graphs, and then take some sort of a limit. So let me describe what actually goes on. Let G be a finite graph, and T is a uniform spanning forest, spanning tree, sorry. Of the finite set of spanning trees that G has, a uniformly drawn spanning tree of G. So perhaps the first theorem that we know about this kind of object that we all understand very well is probably Cayley's theorem, stating that the number of labeled spanning trees of the complete graph has cardinality n to the power n minus 2. And in fact, we understand this object very well because there's a famous theorem of Kirchhoff from 1847 that given any graph allows you to compute the number of such trees by taking the minor of the Laplacian and any minor of the Laplacian and taking its determinant. So when we know how to compute determinants, so this actually gives us a very good algorithm to draw such a graph. But let me present to you another interpretation of Kirchhoff's theorem, actually something that he wrote, that is equivalent to the statement of counting the number of labeled trees. So this goes back to Kirchhoff. I think there are two H's there, no? Yes?
Yes.
Yes. the following statement. You look at an edge, let E be an edge of the graph, and you want to ask what is the probability that this edge is in your uniform spanning tree. So the probability under the measure of a uniform spanning tree that E belongs to T. So this turns out to be something that we can calculate. This exactly is the effective resistance in the electric network between X and Y. So I know that Ori mentioned what is electric networks yesterday. These boards are for like tall, muscly men, not for scrawny Jews. All right.
It's easier in the middle. Pull it up in the middle.
Oh, really? Okay. What, like from here?
No. The center.
Okay. All right. Oh, I see. Okay. So what does this mean? I'm not going to define to you electric networks in the full generality, but the idea is clear. When you have some complicated graph with 2 points. All right, I drew it planar, but it need not be. And you have 2 marked points, and you consider it as an electric network where each edge has a unit resistance. It's a resistor of unit strength. And as we know in electricity, you could take this thing and and perform electrically equivalent operations like the parallel law and the series law to get an electric network that is equivalent to just one edge. And here there is a number, a resistance, which we call the effective resistance. Right, and the operations that you are allowed to do, so this is true also when you put here, not just unit resistances, but also any other numbers. The operations you're allowed to do are basically, very simple things. If you have a network like this with resistances R1 and R2, this is equivalent to the network with resistance R1 plus R2. This is the series law. And if you have a network of this form, the parallel law, R1 and R2, this is equivalent, perhaps I shouldn't write it like this, to the network that has resistance R3, where R3 is given by this formula, the 2. Right, the resistances add in series and conductances add in parallel. So this is very basic high school kind of math, even though I actually have very vague recollection of learning it in high school. I've only learned this in a few years ago, and and we know that there's a lot of connections between this and random walks, and indeed we also know, as we heard in Martin's talk, that there's a lot of connections between spanning trees and random walks. So this is natural to expect something like that. Let's see an example. Right. So an example. So for instance, if you have a finite graph, and this is your edge, xy, and this whole part of the graph is completely disconnected from this part of the graph, then the resistance between this edge is going to be 1. And indeed, a uniform spanning tree, or any spanning tree of this graph, will have to have this edge. So in this case, the probability is indeed 1. Let's consider, so here the probability of this edge is 1. The resistance is also 1. Right? If you have a square, right, and this is your edge xy, then here you have resistance, right? So this is now a network on 4 edges, 4 vertices, and this is equivalent to the network just by performing these operations to the network where here I have 1, and here I have the resistance 3. I just added the resistances using the series law, and now 1 over 1 is 1, plus 1 over 3 is 1/3, which is 4 over 3. So so this is equivalent to something with resistance 3 over 4. So the resistance in this graph between x and y is 3 over 4, and indeed this is the probability that this edge is contained, because out of the 3 spanning forests of this graph, only one of them does not contain this edge. Right? So and in fact, as I said, this statement is equivalent to the statement of counting. Not equivalent in the sense that they're both true. There's actually a short argument that provides, that gives one to the other. So when we have this setting in mind, it's somehow easy to define weak limits of these measures. And indeed, this is something that Pimentel initiated, motivated by some questions of Russ Lyons. And this is now. So now we have G is now our setting. Of course, we're interested in this. We want to deal with infinite graphs. So G is a connected infinite graph. And let's do what is the most natural thing to do. So Gn is an exhaustion. So Gn are subsets, are subgraphs of G, finite, and the union of Gn is G, and I guess Gn they're also monoton. Gn is contained in Gn plus 1. And now, of course, I could draw on each of them the uniform spanning tree and take the limit, right? So Tn is a uniform spanning tree of Gn, right? And I want to take the limit of this, and of course we are probabilists and also adults, and we understand that I've imposed some boundary conditions here. And the another natural thing to do that I'm sure here needs no convincing is to also take different boundary conditions. This is the free boundary conditions where I impose nothing on the boundary. And the other thing I could do, given this Gn, I can form Gn star, which is it's just obtained by G from G. By gluing G minus Gn. So I took all the complement of everything that is outside of Gn, put a single vertex there, and connected it to all the edges on the boundary, right? So the picture will be, if this was Gn, then Gn star will actually be something bigger, right? I'm adding this vertex here and connecting all the edges. And here, all right. Okay, so it's a bigger graph. And we understand that, I may get different, I need not get the same limit. So let's just state the theorem of Pimentel, and let's try to do what, thank you. Right, so the theorem of Pimentel states all right, let's before I state the theorem, let's just say one more notation. So Tn star is the UST of Gn star, and the laws of these. Let's call this law mu n, and this law mu n star. Then Robin proved that in 91, he proved that mu n converges to some mu, and mu n star converges to some mu star for any graph. So what this means is that, or in other words, for any finite set of edges, for any E1 up to EK that belongs to the edge set of your infinite graph, right? You look at the moment in the exhaustion where all these edges are contained, and you look, what is the probability that E1 up to EK is contained in Tn? Right? This converges to some number, right? So this limit exists. So this converges as n tends to infinity for any finite set, and the same thing if I write here Tn star. This converges, and this defines a measure by the Kolmogorov extension theorem. Right? So we have a measure, a measure on subgraphs of our graph G, and it's very easy to see that this measure is concentrated on things that have no cycles, on subgraphs that have no cycles, right? Because if you take a fixed finite cycle in your graph, there are only countably many. The probability that it's there, well, after a certain n, this number will become 0. Right? So for any cycle in the graph, the probability that all the edges are there and the limit is 0. And it's also easy to see that it is a spanning graph, right? Because you look at a vertex and you look at all the edges coming out of it. After, the minute because Tn or Tn star was spanning, then one of the event that all of these edges are not there has probability 0 starting from a certain n. So this would be also something. What is not obvious is whether the resulting measure is concentrated on connected graphs. This is something that is not preserved by the limit. So even though Tn, you look at two fixed vertices in your big finite graph, even though they have to be connected, the path connecting them could go so far away that this information is lost in the limit. Right? So, and this is not a pathology. This can actually happen. So, so what Pimentel proved is when Pimentel studied the case G equals the Euclidean lattice, what he proved is that two things. Firstly, that mu and mu star are equal. And perhaps I should give them names from now on. So mu star is called the. So I'll write this here. Mu is called the free uniform spanning forest. The one we saw. This is the one we saw in the thick lines when this picture comes up, and mu star is the wired uniform spanning forest in the thin lines. Of course, from this picture, you still cannot tell which is which, but I'm telling you this now. We'll come back to this later. So the question of connectivity is, of course, very very interesting because that's the first question that you can ask about this graph. Is it a tree or a forest? And indeed, what he proved is that on ZD, so mu or mu star almost surely, or mu is concentrated on connected graphs, if and only if D equals 1, 2, 3, or 4. And D equals 5, it does not. The graph is disconnected. Okay, and let me tell you why. Actually, for him, it was a little bit. It was a bit of a technicality to prove, but in fact, there is for the wired spanning forest, there is a very nice theorem that characterizes when the forest is actually a tree. So this came up in a very nice paper by Benyamini, Lyons, Paris, and Schramm in 01, which is too many letters for me to write, so I'll just write BLPS 01. And they started systematic studies on these graphs, on general Cayley graphs or on general graphs, not necessarily Cayley graphs. And they have proved the following. They proved two theorems that are relevant for our studies. So firstly, they describe when the wired spanning forest equals the free spanning forest. So mu star is different than mu if and only if G exhibits non-constant harmonic Dirichlet functions, which I'm not going to define to you exactly what it is because I don't really need this, but let me write this down anyhow. If and only if G has non-constant finite energy, Dirichlet energy harmonic functions, which in itself is something that is, given a graph, this is actually something that is easier to check than to check whether these two measures are the same. So this is a useful theorem that we use to check whether the two measures are the same. And they also gave a criteria, which I'll explain to you immediately, for when do you get connectedness for the wired spanning forest. So this is again BLPS And it's the following criteria. The wired uniform spanning forest, or mu star, is almost surely connected if and only if two simple random walks starting from arbitrary points intersect at some finite time. If and only if two simple random walks starting at arbitrary points, arbitrary vertices, intersect. So now we're in a position to understand Pimentel's theorem immediately, because we all know that in dimensions up to dimension 4, two such random walks will intersect, and in dimension 5, this is the first time that we have positive probability that they do not intersect. What is the reason for this theorem? Question? So what I mean here by intersection is that their trace intersect, not that xn equals yn at the same time, rather that there exist two integers n and m such that xn equals ym. Yes, thank you. So this is not what we call collide, this is intersect, which are different things. And indeed, the reason for this is what Martin showed, this is Wilson's algorithm, right? There's a very nice way of generating the uniform spanning tree on a finite graph, which is, okay, in which you pick a vertex which will be the target vertex of your algorithm. You start at any other vertex that you want. You run a loopy race walk until you hit your target vertex. So this will be my target vertex. I run a loopy race random walk from any other vertex to here. And then I start at any other vertex, and I stop my loopy race random walk once I hit this what is already existing, and of course I could create more and more. So this thing also works, at least in the transient case. But what do you do when you have an infinite graph? So this is an observation of BLPS, is that, well, just do the obvious thing, right? Start from, just root it at infinity. So start a random walker at any point that you want. And on the first step, it's a transient graph. It will escape to infinity. And because it's a transient graph, each vertex on your trace has been visited only finitely number of times. So this allows you to actually take the loopy razor of this infinite path. So you get a simple path that goes to infinity. And then just continue doing the same thing. Choose a different vertex, and perhaps it hits the trace, or it probably perhaps it doesn't. Right? In this case, you got two. You will have at least two components, two infinite components. Right? Notice that all the components of the wired and free uniform spanning forest have to be infinite. You cannot have a finite component, because you will see it in finite time, and that means that the exhaustion will not have this property. Right? So this actually gives a proof for this, but of course there's the technical issue that here I had loopy race random walks intersecting, and here I have simple random walks intersecting, but it turns out it's a bit of a technical thing to prove, and this was proved by the same people, but in perhaps a different paper, that these two things are equivalent. So if so two simple random walks intersect, almost surely, if and only if simple random walk and loopy race random walk intersect almost surely, which is what you need to obtain connectivity or disconnectivity. So this is a very nice picture, and we're able, again, this is if you're given a graph, for me to tell whether the wired uniform spanning forest is connected is much harder than for me to tell, are two simple random walks intersect. This is something we could check, but the problem with this is is that there's no such criteria for the free uniform spanning forest. So no such criteria. Criteria. What is the plural? Is it criteria or?
Criterion.
That's a plural or singular? No such criterion for the free uniform spanning forest. Is this grammatically correct? Yeah, I think so. Uh, this is indeed a problem because we have abundance. All you need to have is some harmonic function. So all non-amenable graphs, sorry, not all non-amenable graphs, but many graphs. For instance, in the graph that we've just seen, this does not hold. Sorry, this does hold, and the free and the uniform spanning forest are different. So the Binyamini, Lance, Peretz, and Schramm invested some time in discovering. In fact, let's just see an example where the free and the wired uniform spanning forest are not the same. Just to convince you, and the easiest example is just a 3 regular tree, right? So let's look at this tree, and here's an edge, and it goes up and down because there's inconsistency in the depending on what continent you are, whether trees go up or down from the root. So this is the safe way to draw it, right? This is your edge xy. In the free uniform spanning forest, when you take an exhaustion of this tree, of course, from Pimentel's theorem, it follows that it doesn't matter what is the exhaustion that you take. Any exhaustion yields the same limit. Perhaps I didn't say that clearly, but here, when you take an exhaustion, it's always going to be a tree, and this edge is going to be here with probability 1. Right? But let me convince you that when you take a wired exhaustion, it's actually the probability that this edge is here is going to be less than 1. Right? So these are indeed different trees, and the reason is we know that this graph is this graph here is transient. Right? It's just a binary tree. Right? So the resistance from the root here to this infinity is something bounded. Right? We heard in Ori's talk yesterday that a graph is transient if and only if a resistance from the root to infinity, which is just again a limit over exhaustion, is bounded, and from here to here it's also bounded. So it's not infinity. So that means that this graph, when we wire it, right, when we add this point here and take a big exhaustion, is equivalent to something that here has on this edge xy has resistance 1. And this vertex and this is the same infinity, right? I only add one new point, so I have a point here. Here I have resistance, I don't know, some number c, and here I have resistance c. And the point is that c is not infinity. C is smaller. C is a real number that we can calculate very easily, and this shows that the actual effective resistance between these two vertices is smaller than 1. And so the probability that the edge is here is smaller than 1. So these are different things, and of course here in this example it's obvious that the free uniform spanning forest is connected because it has to be the entire graph. In every exhaustion, it's connected on one graph. It's concentrated on one graph. Right. So indeed, what we see from this example is that we can extend Kirchhoff's theorem to the infinite case. Right. So Kirchhoff, and this is an easy consequence of monotonicity that you have in electric networks, what's known as Riley's monotonicity. So Kirchhoff, for the infinite graph, can be interpreted the probability that the edge is in your forest, and now this may be a forest and not a tree. That's why I'm writing it like this. It may be, well, a tree is a forest, but not vice versa. Is the effective resistance between x and y, the two endpoints of this tree. And the same thing if I had here if the measure was the wired measure, then here I would put the wired effective resistance, right? The same. It's almost the same idea, right? You can take resistance between 2 points in an infinite graph. The boundary conditions actually matter. So this just follows from Kirchhoff's theorem. And I should mention also that it's easy to see that this number is smaller than 1, right? The electricity, the edge, you can always, electricity is the electric flow between the 2 points is the one minimizing the energy, right? And you can always just flow the electricity in probably a wasteful way just through that edge that is there. And there you get energy that is 1. So obviously this number cannot be bigger than 1. Okay. Any questions so far? Okay. So Binyamini, Lyons, Peretz, and Schramm wanted to study this question of connectivity, And as I told you, there is no complete answer to when the free uniform spanning forest. Yes, question.
Is it true in general that mu star is smaller than mu?
Yes, this is also true because the resistance in the wired is always smaller than the resistance in the free, and so that means that you have a coupling. You can couple such that the wired uniform spanning forest is always a subset of the free uniform spanning forest. So I need to say something else. I also need to show you that the probability that two edges are in the wired is smaller than in the, and there's a theorem like that. In fact, it's easy to calculate the probability that any fixed number of edges is in these trees using this theorem called the transfer current theorem, which is a generalization of Kirchhoff. So yes, the wired is always smaller. Okay, so let me tell you, when do we know that the free uniform? So the free uniform spanning forest is actually quite a difficult object because we don't know how to generate it except for by taking exhaustions. And actually there's very little known about it. The only times that we know something about the free uniform spanning forest comes from two reasons. One, it is equal to the wired spanning forest, and then we're in good shape. Or two, we have a planar trick. So there's something about duality that I will show you in a minute that actually helps us to understand it. So it always comes through a connection to the wired uniform spanning forest, which is a much more tractable model. So again, we know whenever the wired equals the free and the wired is connected, then the free is connected. So this is fine. But here are some examples where we know that the free uniform spanning forest is connected when it's not equal to the when it's not equal to the wired. So this is a theorem due to Bignamini, Lyons, Peretz, and Schramm, and also Lyons, Morris, and Schramm. From 08. So when G is planar, a planar Cayley graph that is either non-amenable or let's just write that is bounded degree and non-amenable. And in fact, I will show you an argument for this. So most planar hyperbolic groups, Fuchsian groups, and things like that, when G is planar, I didn't write anything. That is bounded degree. What that is, when G is planar Cayley graph, that is bounded degree. I apologize for the clumsy English. Then the free uniform spanning forest is almost surely connected. I will show you an argument that gives you that, and in fact, it's also clear from what we and this is indeed the case only when your graph is planar, and indeed the duality will play a role, and this is something I will describe to you in a minute. Another case that we know already is Z2. So Z2 is not a non-amenable graph, and if you don't know what non-amenable is, just think about it as very, very transient, or just that the resistance from every point to infinity is bounded above by the same constant for all the vertices, and then they actually know it. In fact, a graph like that has to be rough isometric to two-dimensional hyperbolic space. I can also write here hyperbolic instead of non-amenable, and this will also, and the statement will also follow. So also Z2 is a recurrent graph. The wired uniform spanning forest is connected and equals to the free spanning forest, so it is also connected. So their question was, which is natural question to ask, when we look in the class of planar graphs, we see that the very high dimensional ones, the free uniform spanning forest, is connected. And when we look at the most recurrent graph that we have, it is also connected. Could it be that everything in the middle, the free uniform spanning forest, is also connected? And the answer is, well, I guess let me write down the question first. Question, this is 15.2 in the LPS. Is every plane graph with bounded degrees has that, again, very clumsy English. I'm sorry, it's 6 months in Israel and I forgot everything that I used to know about grammar. Degrees has that the free uniform spanning forest is connected. My grammar in Hebrew, though, has improved significantly. And our theorem is that, yes, theorem together with Tom, which is, we're still writing it, is yes. And in fact, we believe, but we're still working on it, we believe that we can drop the plane and write here planar. But there's still some technical considerations that somehow resemble the technical considerations that you have when you want to prove Kebbe's conjecture about circle domains. So sometimes I'm optimistic, sometimes I'm not about this, but I will be able to update you. For this theorem, we do have a proof, and I intend to show it to you. And before that, I want to explain what is this duality that I've been talking about, and it'll be best to show it in a picture. Where is the picture, though? Here's the picture. No, that's not the picture. Will it be this picture? Oh, yeah. Right, so here, this is a very cute picture. So what happens is that in a planar graph, if you take the free uniform spanning forest, drawn here in white, right? This is a planar graph. This is a picture I shamelessly stole from Oded Schramm. So this picture, or so we think, we actually did not manage to obtain exactly who calculated this who did this picture, but we think it is him. So the free uniform spanning forest here is in white, and you can, when you have a spanning forest of a planar graph, you could take the dual. Every edge that does not exist in your graph, you draw the dual edge, and that gives you a spanning forest of the dual graph, right? And it turns out that the spanning if you dualize the free spanning forest, then you get a new spanning forest on the dual graph, and that one is distributed like the wired spanning forest on your graph. So let me write this down, and this can easily be checked with. So what you see here is that the wired spanning forest. Well, it doesn't look like a spanning forest, but because it has this cycle, the one in red, right? But it's a spanning, but it is a spanning forest of the dual once you identify this whole square into a single vertex, right? So, and in fact, so let me write down this duality statement. Right, and Z2, because the two forests, yes, question. There is no condition. This could be a completely crazy planar graph that I will show you examples of. So the planar graphs are not necessarily Z2 or hyperbolic. You can, in any planar graph, you can, put giant tubes and make it very wildly behave. But of course, as I mentioned in the abstract, there is something that we do know that is rigid for all planar graphs, and that's obtained by the circle packing theorem, which I will show you. So let me just describe to you the duality. So if you take the free uniform spanning forest of a planar graph that the dual is also has finite degrees plane graph, and you take the the dual of it. How do you mark the dual? A star, but then a dagger. My grandmother will be unhappy. So let's put a little Star of David here. So you take the dual of it. This is the same as taking the. So now you get a spanning forest in the dual graph. This is the same as taking the dual graph and taking the wired uniform spanning forest. Right, so this is a statement, and it easily follows just by the exhaustion argument. So let's see it for Z2. If this is a piece of the exhaustion, right, and you draw here on this graph, you draw a uniform spanning tree. A tree. This is a finite part. The dual graph will, will have all these edges inside, right, and everything inside as well. All right, let's draw it. After seeing Jean-Francois draw every piece of that, I feel that I must draw everything, right? But it also has the connections to the outer face. So the outer face in the dual graph, in the exhaustions, plays the role of the wired vertex that we took when we constructed GN star. So all these edges will be here. All right, dot, dot, dot. Sorry, no one's perfect, except. Okay. So this duality allows us, of course, to, so this already explains to you what I need to prove. So indeed, I'm stating the theorem about the free uniform spanning forest because it's the more difficult model. But what this is actually equivalent to is saying that the wired uniform spanning forest. So these are two dual trees to each other. So the wired uniform spanning forest, as in the picture that I showed you, what we have to show that it does not, almost surely does not have a bi-infinite path. A bi-infinite path in a planar graph has to split it into two sides, and so the free, which is the dual, will have to be disconnected. So the wired spanning forest. So let's write this. So this statement, I guess, this statement is equivalent to the statement that almost surely each component, right, where in the setting of a transient, very transient graphs even, so you have infinitely, probably infinitely many components for your wired spanning forest. And what we want to show is that each component of the wired spanning forest is what we call one-ended, what Martin called one-sided, has no bi-infinite path. All right, I'll just leave this here. Okay, so this is the.
I have a small question
Yes.
about the duality.
Yes.
Maybe I should know the answer, but you kind of cheated in that picture because in this case there are no unbounded faces. So
Right.
you require that, or?
No, I do not require, but I require that the graph is. This is where the fact that the graph is plane and not planar comes into. So the same thing works in a tree, which you do have unbounded face, but the setting of this theorem is stated just when this duality works. So if we want to prove it for planar, we do have to do something more complicated.
What do you mean by planar?
Plane and planar.
Yes. I admit that I also asked myself the same question, and due to Tom, I have like the easiest answer. So this is a graph that you can draw in the plane without any accumulation points. That there is a drawing without any accumulation points. Okay, so any tree is going to be a plane graph, and any one-ended planar graph is going to be a graph. Any graphs that you see, but of course you could draw pictures of graphs that I won't show you that have a bunch load of accumulation points. You could draw them with circle packings. In fact, any reasonable set that you give me can be a set of accumulation points for a planar graph. But this is actually some of the problems in turning this statement from plane to planar, which we really want to, because how many theorems do you know that hold for all planar graphs? But of course, then we have to deal with all sorts of very pathological accumulation points, accumulation sets. So indeed, as I hinted, so this is my goal, is to convince you that we know how to prove this. You may be convinced or not in the time that I have. And indeed, the reason that we started thinking about this is I should also add some credit to Omer Angel and Gura Bray, because we working on a problem about random planar maps, and we noticed that we need a lot of there's the free uniform spanning trees are involved. So we really got interested in this really nice model. And at that point, we also knew about the circle packing theorem, which is the point of this talk. The point is, if you want to solve something to do with a probability problem on a planar graph, it actually makes sense to draw it in a good way. And circle packing is one, not the only one, but a nice way to draw a graph that actually gives you information, as you saw in Ori's talk. So let me just remind you with a picture. Is it this picture? No. Before I show this picture, it's probably this picture. No. So is it this picture? Yes. Right, so this picture is a statement of a theorem that goes to Kebe, Thurston, Andreev, and also He and Schramm, and it states that when you have any planar graph with some reasonable assumption, it can either be a finite graph, in which case you can circle pack it on the sphere. Circle packing, just to remind you, is a set of circles with disjoint interiors, and the tangency graph is the graph that you get in which every vertex is the circle, and every edge is two circles that touch each other. So it can either be a finite graph, it can either be, which is drawn here on the sphere, or it could be a recurrent graph and drawn on the full plane. It occupies the entire plane. Or it could be, this is the 7 regular tessellation, or it could be circle packed in the unit disk, so that the accumulation point is exactly the circle of radius 1 around the origin. This you can always do. This is a consequence of this He-Schramm theorem. And indeed, we're interested in transient graphs because the free uniform spanning force is connected on any recurrent graph. So this is actually the picture that we are interested in. But this picture is actually already covered by this theorem because, you can. I just told you that this is the 7 regular hyperbolic tessellation, which is hyperbolic and also non-amenable. So this is covered. This means that every ball here, the radius of it is comparable to its distance from the boundary. But of course, you can have many other crazy circle packings, and let me show you some pictures. Will it be this picture? Yes. This picture is actually a random or semi-random hyperbolic triangulation, similar to what Nicolas constructed, and you can see that you can have very, very tiny circles, and you can put here tubes of circles that make the graph in all sorts of places, very, very recurrent. And this is a bit of a crazy picture. So the planar graph is a wild class. Here's another nice picture that Tom helped me draw. Right, in this graph, the point is the circles colored in red have degree 7, and all other circles have degree 6, but we space it so vastly so that this graph actually from almost every point looks like a recurrent graph, right? Every point here, it looks like even a macroscopic level, it looks like a chunk of the triangular lattice. And so this theorem does not cover this particular graph. So somehow this graph is everywhere you look at, you see a recurrent picture, but in the global scale, or in the big graph, it's actually a transient graph because it is circle packed inside the unit circle. All right. So my goal is to convince you in 10 minutes that we have an argument that shows that the wired uniform spanning forest is connected. Sorry, has no infinite paths. And why do we like circle packings? Well, aside from them having a pretty cool name, they also come useful in one very following way. It allows you, once we draw these circles, we can actually think about the locations. We can think about it in a complex analysis way, or we can think about this. We can think about the shapes that we see. The resistance turns out to be equivalent resistance between two sides of something, an annulus, a square, the resistance turns out to be very close to the conformal modulus of the shape. So in fact, you know very well that if we have, this is an n by n square, and I'm just putting, the usual lattice here, then the resistance between the left-hand side and the right-hand side is just 1. In fact, the electric flow just puts mass 1, electric flow of intensity 1, just puts 1 over n on each of these lines. And you can calculate this exactly. But of course, so here, this is a drawing, a good drawing. I drew this graph inside a square, and this is a good drawing because there is some connection between the conformal modulus and effective resistance. But of course, I could, this is not always hold, right? There could be, I could draw something like this. And in this case, of course, the resistance is very large between the two sides. So what the advantage of circle packings, as you saw briefly in Ori's talk, is that if you have a square or any kind of shape, and you draw, and you have a bunch of circles, these circles are tangent, but ignore the drawing, and this fills out the entire board. But you just look at the square, then the resistance between the right-hand side and the left-hand side is constant. Or any other microscopic shape that the sides are anything that you are convinced an annulus, a triangle, and you want to take the resistance between two sides, this turns out to be a constant. And I can convince you that this is the only place where we use the fact that we are using circles. And then the only reason that we use circles and not any other shapes, in fact, we could use any other shapes. There's like, Oded Schramm has like a lot of theorems about packings. The only thing that we use here is that the radius square of the shape is compared to the area. And I can show you if you want later why this is a very easy, quick argument with electrical networks to compute the electricity. I'll even tell you, you want to construct a flow which will be close to the electric flow from left to right. So what you do is you choose a uniform point here, right? And you just take a path here, a continuous line here, and you take the discrete path of circles that approximates it. This defines to you a random path between left and right, and this tells you in advance. And when you compute energy properties of this random path, any flow can be shown to be a convex combination of paths just like this, and this is a good path, right? It doesn't use any particular edge too much. It splits the energy very nicely, and you can do an easy calculation to compute the energy of this, the way I defined the flow here, to show that the resistance is actually bounded from above. So why does that help us? It helps us because we can now I'll try to draw a drawing that will convince you that the wired uniform spanning forest is a connected graph. Well, we take our graph and we circle pack it in the unit disk, right? Because we're interested in we are interested in transient graphs. So such a packing always exists. This is the one place that we use the circle packing theorem. So I will draw this is the unit disk where everything, all the little circles are drawn. I won't continue this drawing, and of course it accumulates to everything. And now I choose a particular, so I will not draw the inside circles, I will just look at this. I look at a particular edge, and I want to say, what is the probability that this edge has two infinite paths, one disjoint paths, one going from here, and the other going from here, in your tree. I want to show that this probability is 0. I'll show this is true for any edge that I choose, because there are countably many edges, the result follows. So assume this doesn't, assume this is the picture that you see. If this was the picture that you see, you can actually perform an exploration process in very similar fashion to what you would do in two-dimensional critical percolation. You will just, from this side of the edge, so this will be x and this will be y, from this side, I'm just going to find out, since I never check the status of this edge xy, and I'm exploring with a BFS procedure my tree coming out of y. but I want to look at the rightmost path. So every time I check, is this edge here or not? Perhaps it is. And now I will go as right as let's go as left as I want. Perhaps it'll be better for the drawing. So I can always discover the interface. Let's say it's here, but of course during this exploration I could have discovered another sub-finite tree here or something like that, like this. I haven't ruled out the probability, the event that I have many paths. So here I will discover some closed things, and I want the infinite path that is the leftmost with respect to this orientation. So here it is, and I stop this process when I get epsilon away from the boundary. So here is a picture of what I've seen. So I've exposed both the status of open edges that are in the red is the edges that are in the forest, and the yellows are the edges that are not. Right? So here's what I did, and from here I choose the rightmost path. Right? I look at here, and I may have discovered like all sorts of things, but everything here is closed. I cannot take this infinite red path to be more left than what it is, because it's blocked by white edges that are not in the tree. So if the bad event happens, then I see something like this. But now I use Kirchhoff's law, right? I condition on what I see. Now there's a fact about trees. If I know that all these edges are open, if you condition in a finite graph on this edge being in the tree, you can contract it, and then draw in the graph that you have obtained, you draw the uniform spanning tree, and then put this edge back, and you get a uniform spanning tree on the original graph. This is very easy. So we can consider all this red as just one vertex, and we want to show that the resistance between these two vertices is small, because that's the probability that the edge will be there. And we have this picture, and here we haven't discovered anything. So here, this is all parts of the graphs we have not touched. So we are essentially drawing a uniform spanning tree with this one edge and everything here not touched. So let me convince you now with a simple drawing that the resistance is small. The radius here was epsilon. I put annuli, growing annuli, that touch here one side, and here infinity on the other side. And I remember that I'm in the wired spanning forest, so the infinity is just one vertex. By the circle packing argument, the resistance here is constant, and here it is constant, and here it is constant. So I have a parallel law, right? So what I get is that the resistance between x and infinity is very small, right? Because I have here log of 1 over epsilon annuli that have a bounded resistance. And I do the same thing here. Right? And I get that the resistance from x to infinity is small, the resistance from y to infinity is small, but infinity is the same vertex. So by the triangle inequality, the resistance between x and y is also small. Hence, the edge will be there with very low probability. I'll be glad to show you more details of this if you would like. Let me finish here. Thank you.
Are there any questions?
Is there any, maybe it's very stupid, but do you know any example of graph where both have, both are disconnected?
Yes. So I should have said that earlier. This whole argument is planar in its nature because planarity is really used. But in three-dimensional hyperbolic space, which is a very high-dimensional graph, they turn out to be, the wired and the free turn out to be the same, and they are both disconnected. And there are many, many such examples.
Any other question? So I guess you really need bounded degree for this proof. And is it true without the bounded degree condition?
It is not true without the bounded degree condition. In fact, here here I worked in the dual, what I actually used here is bounded codegree. This whole argument did not rely on bounded degree in this fact, but it's easy to see that if you take Z2 and put on, say, from here to here, you put a drift. On this edge you put 1, weight 1, this edge you put weight 2 and 2 to the n, and you say here you put another drift like that, then you can convince yourself that with probability 1, the free uniform spanning forest will not be connected. In fact, there will be a component. Just run Wilson's algorithm rooted here. So this part will be here, and this part, in order to get to here, will go down and then bounce around until it hits it. So these two vertices will not be in the same connected component of the free uniform spanning
I
forest.
think the weights have to go super exponential.
Super exponentially? That's okay. I accept that without knowing, based on nothing.
Okay, let's thank Asaf.
Thank you.
We'll take 10 minutes break.